Waking up feeling heavy, muscles taking an extra day to bounce back. We all know the physical toll of getting older, but aging is a broad, abstract concept. Behind that feeling of fatigue is a highly specific, measurable deficit happening inside your body. To understand it, you have to look past the muscles and bones, down to the billions of individual cells doing the work. When you feel that systemic exhaustion, you are experiencing the macroscopic symptom of a microscopic bankruptcy. Your cells are running out of the molecules required to keep the lights on. This diagram shows what scientists call the hallmarks of aging. It maps out 9 specific interconnected networks that break down as we get older. Out of these 9 failures, 2 sit at the center of the cellular energy crisis: mitochondrial dysfunction and deregulated nutrient sensing. The link connecting both of these failures is a single molecule called NAD+. NAD+ has 2 vital jobs. It helps convert food into ATP, the chemical energy your cells run on. Simultaneously, it provides the fuel for the proteins that repair your DNA. By middle age, our natural supply of NAD+ drops significantly. When that happens, the system loses its primary currency. Inside almost every cell are mitochondria, the tiny engines responsible for generating power. They strictly depend on NAD+ to run. As your NAD+ levels drop over the decades, these engines begin to starve. The production of ATP begins to stall. A starving mitochondrion malfires, leaking highly reactive oxygen molecules, often called free radicals, or ROS. These reactive particles act like toxic pollution inside the cell. They bounce around erratically, fracturing DNA strands and degrading internal structures from the inside out. The failing cellular engine is now actively destroying the factory itself. Under normal conditions, the cell has a repair crew to handle this kind of damage. These are a group of longevity proteins called sirtuins. Sirtuins are strictly NAD dependent. They cannot function without it. Because the mitochondria already consumed the dwindling NAD+ supply, the sirtuin crew sits idle. DNA damage is left unrepaired. If a cell allows too much DNA damage to build up, it risks mutating into cancer. To prevent that, the cell triggers a permanent, irreversible shutdown. This shutdown turns it into a senescent cell. These zombie cells stop dividing but refuse to die, secreting toxic inflammation into the surrounding healthy tissue. The energy crisis is now systemic. The power is out, the repair crew is dormant, and the cell poisons its neighbors. Can this cascading chain reaction be stopped? Scientists have observed that strict fasting or caloric restriction forces the body into a survival state that naturally boosts NAD+ and clears out cellular waste. The problem is that chronic starvation is physically miserable and for most people completely unsustainable. To solve this, researchers identified caloric restriction mimetics. These are molecules that trigger the exact same metabolic pathways as fasting. They shift the cells into a highly active, youthful repair state without requiring a change in calorie intake. The most direct of these interventions are NAD+ precursors, like nicotinamide riboside, NR, and nicotinamide mononucleotide, NNN. Instead of relying on the body's complex internal assembly lines, these precursors bypass the tangled metabolic pathways. They provide the cell the raw building blocks needed to synthesize fresh NAD+. With the supply restored, the cascade runs in reverse. Fresh NAD+ feeds starving mitochondria, allowing them to produce clean ATP and halt the leak of toxic ROS. This surplus allows dormant sirtuins to resume their work, zipping fractured DNA strands back together. Once the cellular factories are running efficiently again, the burden of zombie cells begins to clear and systemic inflammation drops. Aging is no longer an inevitable decline. It is a metabolic pathway that science is finally learning how to refuel and regulate.